Okay, welcome everyone to today's a16z crypto research seminar. Very pleased to introduce Mahimna Kelkar, who was our very own intern from 2 summers ago. He's just wrapping up his PhD right now under Ari Jules' supervision at Cornell. He's worked broadly across the blockchain space, consensus, cryptography, now increasingly game theory and mechanism design. So welcome back. Very excited to hear about Rethinking Crypto Attacker Models.
Thank you for the introduction. Yeah, really excited to be here again after, as Tim mentioned, being an intern 2 years ago. Today I'm going to talk about rethinking crypto attacker models, a little bit of a technical talk, a little bit of a philosophy perspective as well. So it's kind of no secret, for the past 15 years, blockchains have seen a sort of meteoric rise. I mean, that's kind of why we're all here. From Bitcoin, if you look at, in 2008 or 2009 as sort of a cryptocurrency that didn't require centralized coordination from the government, to now sort of thousands of companies, hundreds of millions of users, and a lot of applications way beyond just cryptocurrencies. But from sort of an outsider's perspective, there's this dichotomy that's usually associated with blockchains. So on the one hand, you have this sort of trillion-dollar potential impact applications in fintech or decentralized finance with things like election transparency, legal industry with smart contracts, even something like gaming. But on the other side, there's also this trillion-dollar hype phenomenon where you have constant articles on the price of Bitcoin today or what the last NFT sold for, or even things like outright scams, which lead to 25 years in prison, for example. So how do we sort of deal with this trillion-dollar impact question versus trillion-dollar hype? So the question we want to ask is how do we get mass-scale adoption of blockchains? So there's a few different things that we can try to think about how we get mass-scale adoption. So the first obvious thing is, of course, performance. We have this great functionality that blockchains can provide us, but how do we scale this in a way that's practical for millions of users? The other interesting thing is regulation. How do we separate sort of the noise from the real applications? And that's something that can potentially be done with regulation. But today, what I'm going to focus on is this third aspect of security. So what does fundamentally blockchain security and the security of blockchain applications even look like? And my sort of central claim here is that one reason why we see a lot of attacks on blockchains, a lot of skepticism associated with blockchain protocols in general, is that even as researchers, we don't fully understand how to secure blockchains and their applications. So blockchains, from a traditional system security aspect, operate in a completely new setting. So it's completely new sort of decentralized setting that is very different from the applications we've built from a classical security sense. There's sort of these complex interactions between different protocols, different security models, incentives come into play, for instance. And the other kind of thing is we're building these protocols in essentially the wild. So any design vulnerabilities that pop up, so design flaws, not just program errors, but sort of these complex design flaws that pop up, can be effectively monetized by attackers or anonymous attackers trying to steal from these applications. And we've seen a lot of these attacks in the wild on blockchain protocols where complex interactions between different, for example, DeFi applications have resulted in millions of dollars of loss. The real point here is that blockchains sort of fundamentally intertwine many different research areas. So we know things about cryptography and distributed systems, which are often used for just building secure protocols in the modern system security context. But now for blockchains in particular, we've had to think about mechanism design, game theory, even things like macroeconomics, because blockchains come with this built-in money aspect. But moving forward, we also want to think about governance, how to do sort of these DAO protocols with social choice, and potentially many more, maybe from a legal context, for example. But one thing's sort of true, that security can no longer be thought of in just one vein. We have to sort of think about security more holistically. And that's kind of my fundamental thesis here. It's the purpose of this talk is to argue that we need sort of a first principles approach to designing these secure protocols, even thinking about what security means in the decentralized context. This isn't meant to be sort of an approach to defining what security means. I think we're sort of really far away from combining these different areas into one seamless model. But it's more so about giving examples from my research of what can go wrong when you sort of try to meld models from different fields. So I talked about using cryptography, distributed systems, mechanism design, and a lot more in this talk. So I'll talk about sort of a couple learnings from the research. The first learning is that security in these decentralized settings has a lot of novel challenges. And in particular, I'll show sort of new attacks that make us rethink how we define security because they work by violating under specifications and implicit assumptions in the models of security that we've thought of. And the learning number two is that understanding how to secure blockchains and their applications has broader utility, even for the purpose of sort of modern system security. And I'll show this by showing sort of new insights of how thinking about blockchain security can provide on just normal general security models. So in this talk in particular, I will talk about two works of mine. And these are sort of new attacks that make nefarious use of emerging technologies. And these are motivated by blockchains, but the impact is potentially much broader. The first attack I'll talk about is what I'll call new encumbrance attacks that make nefarious use of trusted execution environments or multi-party computation protocols, which are typically used for building secure applications. And this actually ends up providing new insights onto how cryptography defines knowledge and this proofs of a knowledge primitive itself, and we provide a new kind of knowledge definition called proofs of complete knowledge. In the second part of the talk, I will mention new attacks on accountable cryptography by making nefarious use of blockchain smart contracts essentially as a coordination mechanism between attackers. And this will provide new insights onto collusion and incentives in general amongst cryptographic protocols. Okay, so let's get started. The first one I'll give is these encumbrance attacks and definitions of knowledge in general. So sort of a common intuitive goal that's followed for a lot of these cryptographic protocols is the following. So usually there's a completeness-like goal which says that an honest user who knows the key will succeed in the protocol. And there's usually a soundness-like goal which says that an adversary, and this is a person that doesn't know the key, will fail. But what does it actually mean to know this key? So here's sort of the implicit mental model that we think about when we design these protocols. So Alice knows this key if she can explicitly furnish it as private input to a protocol. So for example, if you have a protocol with some step where Alice computes an output with some function of the key and an input, and then sends it over to a remote party Bob, what you kind of think about in your mental model is that Alice has this key and input locally in her state. She computes the function locally and then sends it over to Bob. But what I'm going to show is that there's actually a subtle discrepancy in this mental model that leads to a new class of what I'll call encumbrance attacks, which eventually lead to new insights on how we define knowledge within cryptography. And here's sort of the high-level picture of encumbrance. On the left side, we have this protocol expectation of the key and input being held locally by Alice. And on the right, in the encumbrance setting, what we're going to do instead is that the key is going to be locked inside of this lockbox instead of being owned by Alice. And access to this key is going to be partial and hidden in this lockbox. So Alice can query the lockbox with the input and get some response from it. And what I'll call these new encumbrance attacks is that, in fact, locking a key in this way, in a partial way, in a hidden way, can break protocol guarantees because the protocol cannot distinguish between the expectation world and the encumbrance world. And what's more interesting is that this lockbox can be instantiated through sort of common security tools like trusted hardware and MPC. So just to give some background on TEEs, I'll illustrate some concrete attacks after this point. But just to give some background on TEEs, everything I'll say will also apply to sort of MPC-based attacks. But for concreteness, I'll talk about TEEs. So very sort of informally, trusted hardware, trusted execution environments are sort of these tamper-proof hardware components built into the CPU that can hold sort of private data and do sort of arbitrary computation on it. And these are sort of becoming popular in industry with things like Intel SGX or ARM Trust Zone or AWS Nitro. And kind of the property that these provide are as follows. So there's usually an integrity property, which means that even the operating system or other programs that are running on the computer can't tamper with the control flow of whatever program is running. And there's like a privacy confidentiality property, which says that even the operating system or other processes can't learn anything about the internal state of the program or sort of the data that's held inside of this trusted hardware. Now, in the context of encumbrance, what we're going to do is essentially place this key inside of the trusted hardware box. So we'll actually just generate the key inside of the trusted hardware itself so that only this trusted hardware knows what the key is. And the idea here is that the program of the TE will restrict access to this key. And this is where our encumbrance attacks are going to come from. The typical assumption that's made in a lot of protocols is that a user won't share her key. And this is kind of natural to make because if I share my key, then whoever I share to can just completely impersonate me. They can steal all my money, they can take my identity, and so on. So usually there's this assumption made that a user won't share her key. But what encumbrance allows this user to do is sort of share or rent partial access to different functionalities of the key. So because the key is held inside trusted hardware and nobody knows the key, and you can use the program to restrict access or split access to the key, what you can do is keep only the access or the functionality that you want and sort of rent or sell any of the functionality of the key that you no longer care about. And here I'll also sort of mention that all of these attacks are essentially caused by the user willingly encumbering her key and colluding with the adversary in some sense. I'll give some sort of concrete, powerful attacks. The one I'll start with is sort of a powerful attack on blockchain voting in a way that kind of gets around all prior work on coercion-resistant or bribery-resistant voting. So in a blockchain context, you can typically think about a user's wallet or key, let's say, having two use cases. One is it has some money that the user can spend. And the other is, let's say, the key also allows the user to vote privately on a proposal in, let's say, a DAO. Now, suppose that Alice is willing to be paid for her vote. She cares about her money, but she doesn't actually care about her vote. So she's willing to just be bribed or paid for whoever the briber wants to vote for. Now, in some sense, Alice can't just give her key to the briber, because if she does that, then the briber will just steal her money. But with encumbrance, Alice gets a new power of collusion with the briber. So what Alice can do is she willingly encumbers her key inside of this TE and installs a vote by program as follows. So the program still allows Alice to spend her own money. So it will sign any transactions that deal with the spending of money. And for this particular election, it will only sign messages that correspond to voting for the candidate of the briber's choice. And what ends up happening here is that this is essentially a way for Alice and the briber to trustlessly collude to exchange a bribe for a vote. Now notice like Alice is okay with the bribe because she only cares about her access to her own money. She doesn't care about the vote. She's willing to be paid for it. And she still has access to her own money here. And the briber is okay with this because Alice provably can only vote for his candidate of his choice. And she can't sort of double cross him and vote for someone else. So he's okay with giving the bribe as well. And it turns out that this breaks a long line of prior work on coercion-resistant voting, mainly because there are implicit assumptions in all of this work that the user Alice has full access to her key at some point. Typically, this is during some sort of registration phase before the adversary comes in, or sometime after the voting, whether the adversary has gone away. But at some point during the protocol, it's sort of implicitly assumed that Alice has full access to her key. And this assumption is violated if the key is held inside trusted hardware in the first place. And what's interesting is you can sort of generalize this attack to create sort of hidden marketplace, which can anonymously connect voters who want to sell their voting power to bribers who want to buy this voting power. So it's anonymous in the sense that these voters and vote buyers don't need to even know each other. And hidden in the sense that it's hidden, its identity is hidden from the voting platform itself. And we actually built a prototype of this in a recent work and called it essentially a dark DAO. We also wrote this sort of recent paper on all kinds of shenanigans that you can do with this sort of encumbrance. Essentially, the idea here is violation of what we call the single entity address ownership assumption, which is pervasive in a lot of protocols. The idea that one private key means one owner. And this is something you can violate using encumbrance, right? If the key of the account exists inside trusted hardware, the program can allow you to essentially split access between different parties in a completely undetectable way. So for example, if you have an account with 5 ETH, that doesn't mean that you have 5 ETH, right? It could be that you only have 1 ETH out of it, someone else has 2 ETH, and then someone else has the rest of the 2 ETH. Yes.
All these conditions need to be chosen a priori, right? So you need to hard code them into the TE. For instance, the candidate you want to vote for. So it's not something you can adjust. So if I'm an adversary and I want to buy your vote for a specific candidate, and in a month I want to buy another vote for another specific candidate, we need to agree at the very beginning, right? We can't adjust it on the fly.
So, so in this new work, basically, we developed sort of a policy engine that essentially you have some starting state and then you have like a transition function of what you can change the policy to. So in the case of voting, for example, if there's like a voting window that's only open for like a week, then you can at the start of that week have a bribe for that vote period. If the vote is like open indefinitely, then you'll have to agree to it before that sort of begins. But if it's sort of like a bounded window, then you can kind of agree to it as like the new voting period is going on, essentially.
And you can verify that.
Yeah. So the only concern is like any access that you have right now. So let's say I can sign a vote right now, but I should not be allowed to do it later because someone's going to bribe me for that vote. That's sort of the only attack vector in some sense for this like policy engine. And you can sort of prevent that in natural applications where I can't sign a message for voting on something 2 weeks from now because that proposal itself doesn't exist. Right? So when that proposal exists, then you can create the bribe at that point. So it doesn't have to be fixed at the start. One kind of really cool thing that's applicable here is the idea of selling unvested tokens. So the kind of example here is as follows. Let's say you have a VC investor who wants to invest in a startup, in particular wants the startup founder, Alice, to be incentive aligned. And the typical approach you can do here is like the founder tokens are locked for a certain amount of time, so they can't sort of dump their tokens and be detached from the success of the protocol. But what you can do with liquefaction, or this encumbrance phenomenon, is it can allow this founder, Alice, to privately sell her unvested tokens. So the idea is the tokens, locked tokens through the smart contract on chain, they will be held inside a T encumbered address, so an address whose key lies in the TE. And now essentially selling this token privately just corresponds to changing the owner in the trusted hardware. And nothing will be visible on chain, so sort of the founder can just sell all of her tokens privately to a third party without sort of the VC investor realizing this.
Sorry.
Yep.
Do TEs have access to secure randomness?
Yeah, they should.
Okay.
Who controls this TE?
So yeah, that's a good question. So basically, we actually developed this on a TE blockchain. We developed it on Oasis, which is sort of, you can think about like a decentralized TE blockchain. From a theoretical standpoint, all of this can be done with a single TE that is assumed to be live. So let's say it's held by someone and they're assumed to be live for any responses. And basically, to get rid of that liveness assumption, you're just decentralizing the TE. So it's sort of like a network of TEs that simulate a single TE. So there's this platform called Oasis, which essentially functions as this TE blockchain. Another sort of really cool thing here is this demo that we created called takemyape.com, which I encourage you to take a look at. And the idea here is we actually bought an ape for this demo, and we allow you to own the ape, not just rent it, actually own the ape for 15 minutes. And the way it can work is as follows. So we allow you to create an encumbered account, so an account whose key is inside of a TE, and we transfer the ape to that account. But the account doesn't allow you to transfer that ape outside of it. But you can still prove your ownership of the ape to the Bored Ape Yacht Club. And essentially, from the chain's perspective, you are sort of the owner of the ape just for the 15 minutes. And only you can sort of prove access to the account. So you can essentially own an ape for 15 minutes for something like $2, basically the cost of a transaction, which is something really cool.
So what enforces that after 15 minutes it gets transferred back? Or
So the way we have it is basically anyone can transfer it from that encumbered wallet to their own encumbered wallet after 15 minutes. So you kind of need to have enough gas, like we ensure that you have enough gas for someone else to also transfer it out. But you could also do it so that it transfers back after 15 minutes. It's just this is more gas efficient.
It feels to me like the T's are more of a means to an end here. Like what you're really worried about is the fair exchange problem in some sense. You're saying in a world where people can do fair exchange, the definitions we have for what it means to know things are wrong. So am I correct that you don't really need TEs in some sense here?
Yeah, I mean, basically, even fair exchange is kind of like, usually assumed to be done with some sort of trusted party.
Sure.
Okay. But essentially, this is even more, it's like sort of more complex forms of fair exchange, right? Because it's sort of any arbitrary functionality of the key.
I see. Not just like oblivious transfer.
And the other thing is, if anyone physically owns the key, then they can do everything with the key, right? So this is sort of a fair exchange of like limited functionality of the key that nobody has access to, essentially. So it's not really an exchange of that sort. It's not that I have access to some functionality that I'm giving to you. It's like even I don't have access to that functionality because it's held inside of a TE. So there's a little bit of a difference there.
So basically, so all this has is kind of like a timer to ensure that you get it at least 15 minutes. Is that right?
Yeah. Basically.
But then after that, anyone can
take it.
Take control, as you say.
Yeah.
Okay.
So it's like, I really encourage you to go take a look at this website. And we actually bought like a 14 ETH ape for this, which was kind of fun.
I think it's important in your model that Alice doesn't have the key herself.
Yes.
And only has the key inside the TE. How is that enforced?
So basically, the key itself is generated inside of the TE, and the TE will prove that the key was generated inside. Yeah.
Wait, why is that important? I think that's the essence of what I'm confused about as well.
Right. So the idea is like if I have the key outside of the TE, then I can do everything with that key, right? Like I can sign arbitrary messages with that key. I can do arbitrary transactions with that key.
True. I thought the concern was that the people that don't have the key can solicit services of someone that does have the key to prove that they know the key for some specific application.
So it's the thing that when I'm actually, so I'm not like renting it to you, right? I'm actually giving you ownership of it in that I don't have control of it myself. So the idea where these encumbrance attacks comes from is it's not that I'm giving you access to the thing that I have access to currently as well. It's more that nobody has access to it except for you. Even I don't have access to it. So if I had access to, for example, voting in the voting example, and I give you access as well, you're still not convinced that I'm just not going to sidestep you and vote on my own. But if the key is inside of the TE, I physically can't vote because I don't have access to that functionality at all. Only you do, right? So you're sort of guaranteed that the vote is only going to happen according to you. There's a lot of powerful attacks that we found both within and beyond blockchains. So for example, you can break deniability in end-to-end encrypted deniable messaging platforms. I showed you like the bribery on bribery-resistant voting. You can sort of sever the soul of soul-bound tokens by making them not attached to a single account anymore. You can transfer sort of these designated verifiable proofs, which are supposed to be non-transferable. You can have undetectable renting of account credentials and reputation. Like if you have a Twitter account, you could rent it out so that someone else can tweet on your behalf, for example. You can rent reputation. So if there's like an application like Uniswap that's giving you a better trading price for frequent high volume traders, you can rent that reputation to someone else in a trustless fashion. You can do things like wash trading in more complex ways, like you can fake theft of your funds. You can do sort of more hidden privacy pools like Tornado Cash, for example, that are more undetectable to on-chain snoopers. But in general, sort of what we show is that these seemingly unrelated attacks can be unified essentially by identifying a problem with the way we define knowledge. And sort of just to take a step back and understand the root cause of these attacks, here's sort of the high-level description. So in the normal scenario, as I mentioned, where the key is physically held by Alice, you can intuitively say that Alice has knowledge of the key. But in the encumbered scenario, intuitively you want to say that Alice doesn't have knowledge of the key. And so this like proof of knowledge primitive seems purpose-built to distinguish between these scenarios. In one case you have knowledge, one case you don't. But the reality is that this proof of knowledge protocol can be successfully completed exactly the same way in both scenarios. And the sort of insufficiency comes from a very subtle understanding of this proof of knowledge primitive. So just to give a brief background, so in a proof of knowledge primitive, you have a prover who wants to convince something to the verifier. Essentially, the prover wants to convince the verifier that she knows some witness W for this public statement X being in a language. So typically some NP language. So the high-level example that you can think about for this is, let's say, the knowledge of a secret key corresponding to a public key that's known to the verifier. And usually you have a completeness property that needs to hold, which just says that an honest prover can convince the verifier. And a soundness property, which is the thing that formalizes the knowledge part, says something like, if a prover convinces the honest verifier, then there's this efficient extractor machine that can interact with the prover and recover the witness from the prover. And this extractor can be sort of white box or black box. It can interact just with the prover in an oracle fashion, or it can even have access to the code. But regardless, there's this sort of extractor machine, and this is how knowledge is defined. And it turns out that this is actually where the problem lies that enable these encumbrance attacks. So the high-level idea is that this extractor is sort of a theoretical proof construct, and sometimes it can't be run in practice even given arbitrary time because of things that exist outside of the model. So for example, in our trusted hardware use case, if the TEE holds the secret key, then the hardware assumption itself prevents extraction outside of the TEE. Or as I mentioned, you can also do this encumbrance using multi-party computation, where here each party individually holds a random looking string, but they can be combined together to reconstruct the key. And essentially here the extractor requires access to all of these parties in order to be able to extract out the witness. But in practice, it's only given access to one of these parties. So even if it was given arbitrary amount of time, it still wouldn't be able to recover the key. And this is sort of this gap between theoretical modeling and reality, which leads to these encumbrance attacks. I'll talk about our work on proofs of complete knowledge. And sort of the core idea here is we want to instantiate this extractor as a physical entity instead of it just being a theoretical proof construct. So here's sort of the mental model, so that you have a prover trying to do a proof of complete knowledge to the verifier. And we have this sort of new resource assumption-based formalism. So the reason for that is basically you can't get a proof of complete knowledge in the standard model because any operation, anything that you can do inside of a TE, you can do outside of a TE, and same thing for MPC. So basically, you wouldn't be able to distinguish it just based on that. So we have this sort of new resource assumption-based formalism as follows.
Just a question, I don't know if that makes any sense. Like a TE usually has a specific functionality.
It's usually a general purpose thing, so you can have an arbitrary program in the TE.
But like it's a specified program before I build the TE in some sense, right? Like what if I define proof of complete knowledge to mean like the adversary chooses a functionality, and then I need to run that functionality on the key, it's sort of like not allow you to design the TE expecting what functionality I will expect you to do.
So the TE can take in an arbitrary
program,
general
like
program.
a universal.
Yeah.
I see.
And then basically what it does is it has this functionality of remote attestation where it can prove that it ran this program on this input and this was the output. Right? But then you can load it with a different program, for example. So the idea for this resource assumption-based formalism is that an honest prover will only be allowed to use the set of approved resources, say are honest. The adversary can use unapproved resources as well, but only those that are considered practical. So this is sort of where our hardware assumptions will be baked in. And now the idea is this extractor, instead of being a theoretical proof construct, will be the physical channel that connects the prover to the resource. And the idea here is that if the prover can convince the verifier of a proof of complete knowledge, then the witness will be exposed on this physical channel, allowing the extractor to extract it. So essentially, the prover can convince the verifier only if it has unencumbered access to this witness. So if you look at the formalism and try to compare between the proof of knowledge and proof of complete knowledge, there's actually very little delta of adding this resource-based formalism. So if you look at the completeness property, we can just say instead of just the honest prover convincing the honest verifier, it does so using one of these approved honest resources. And now what the soundness property says is that if a prover convinces the honest verifier using a practical resource, so this is the resource set that sort of encodes our hardware assumption, then our extractor can recover witness from the channel between the prover and the resource where this extractor will lie.
The CK soundness definition doesn't capture the fact that there could exist some P star that convinces me using some other resource.
So that's why I said there's this set of all practical resources are pract, which is larger than the set of honest resources. So it can use any arbitrary resource that it wants,
Okay.
as long as it's practical. And that's sort of where a hardware assumption is baked in of what resources are considered practical.
And how is there a formal definition of rpract?
So it sort of depends protocol to protocol, right? So even the set of honest resources is like, okay, for this protocol, this is the resource that the honest user will use. And now the adversary is allowed to use any resource as long as it follows some practicality thing, like it doesn't compute too fast or something like that. I can mention a little bit more about that when I talk about the protocols. Okay, so I'll just provide one example of a proof of complete knowledge protocol and very brief overview of this. So the intuition here is that you take a Sigma protocol, which is this common 3-round proof of knowledge design, and you combine it with a Bitcoin style proof of work mining. And the idea here is that this proof of work ASIC will be used as the hardware resource. And the hardware assumption here will be that the proof of work ASIC is much, much faster at computing hash functions than any sort of trusted computation that's CPU or GPU based. So essentially, the set of practical resources are you can use anything as long as it doesn't compute hash functions very, very fast and can be encrypted at the same time. So that's sort of the hardware assumption. So intuitively, the protocol looks as follows.
Sorry, don't you need a bit more that you can actually tap that channel between?
So basically, the channel is basically the wire that connects the prover to the resource, which we assume to be visible to the prover. So it's sort of in the local domain of the prover. Think about the wire that I used to connect the ASIC to my computer.
But why is this equivalent to the ASIC resource?
Can you repeat the question?
Why should I assume that because you have an ASIC, I have access to this? I don't see the connection there.
So essentially, the channel is sort of the physical wire that connects my machine to the ASIC. So it's sort of being plugged on my local computer where I'm trying to do the proof. So the assumption is I can view it. Right.
But that's not the only kind of ASIC one could build, or is it?
I mean, you have to connect it to some computer in some sense, right? And that's sort of the extractor.
What if the ASIC itself had the TE?
Yeah, then this would, if the ASIC itself can be encrypted.
In some sense.
Right, and it can basically do still as fast computation.
Sure, yeah. The TE does a fast computation basically.
Right,
now.
so then this would break the protocol. But that's sort of part of the practicality assumption that you can't, or there currently at least doesn't exist.
Okay, so rpract basically captures this.
Exactly.
Okay,
yeah.
cool.
So basically the idea is you have a Sigma protocol between the prover and the verifier that generates, say, some transcript T. And the idea is you want to embed this transcript T into a proof of work mining puzzle. So you want to try to find a nonce that such that the hash value of this T comma mu is less than some difficulty parameter. So I'm kind of hiding over a lot of details here. But basically the idea is once you find that nonce, the proof just looks like the transcript and the nonce that verifies the proof of work puzzle. Essentially the idea here is that we use the resource in such a way that the witness will be leaked onto this extraction channel using the special soundness property of the Sigma protocol. And essentially the security property that we get is that the prover can't convince the verifier unless it has sort of unencumbered access So sort of like this witness is revealed on this channel between the prover and the resource. So let's look at the case where the prover is malicious. It's an encumbered prover where the witness is held inside of the trusted hardware box. So in the first case, if the encumbered prover still uses the ASIC hardware, then the special soundness property of the signal protocol will still kick in, and we'll be able to extract the witness out here in plain text. Otherwise, if it doesn't use the ASIC resource, it just tries to compute the hash functions locally inside of the TE itself, then because of the resource assumption we have, the prover won't be able to complete the proof of work in time, so the verifier will reject. And kind of the high-level takeaway here is that if the voting platform requires a proof of complete knowledge from the user, then they can be guaranteed that the user owns their key, and sort of can't sell access to her vote without also losing access to her wallet, which is basically the thing we wanted. So kind of just to summarize this part, I showed sort of these new encumbrance attacks that exploit subtle gaps in the way proofs of knowledge are defined. And I defined this new proof of complete knowledge primitive, which we showed to be necessary to prevent these attacks.
To what extent do you have intuition about how much harder it is to get this sort of complete knowledge property versus knowledge, right? So like I could imagine even a black box positive result. Like whenever you can get proof of knowledge, you do something with the proof system and under assumptions about rpract or whatever, you also get complete knowledge. Or maybe there are like separations between the two. I have no idea.
Yeah, that's a good question. I don't know too much about how that would pan out. So one thing we show is you can take any Sigma protocol that's specially sound and do it, construct a proof of complete knowledge this way. There's also a simpler proof of complete knowledge where we use a trusted hardware as the resource itself, with the assumption that you can't simulate a trusted hardware inside of another trusted hardware, whatever that means. But we wanted to define it in this sort of broad resource-based formalism because it allows for other resources that we haven't been thought of to create new, say, complete knowledge protocols.
So if I wanted to deploy protocol, I would want to prove both soundness and complete knowledge separate, like the two definitions separately is what you're saying? You're saying they're incomparable, the standard definition of knowledge soundness and complete knowledge? Or?
No, I mean, in some sense, the complete knowledge is
going to imply the knowledge
is going to
soundness,
imply,
right?
yeah.
Okay.
So it is a proof of knowledge in some form, yes. Cool. Okay, so the second thing I'll talk about is sort of these new attacks on accountable cryptography that make use of smart contracts, essentially for coordination purposes. So there's a lot of these sort of multi-party cryptographic protocols or multi-party protocols in general that make some sort of honesty assumptions on quorums of participants. So for example, you can have a protocol that works when there's, say, 2 out of 5 nodes that are corrupt, but doesn't work when 3 out of the 5 nodes become corrupt. And kind of a high-level question or a natural question to ask is, can we detect protocol failure of this form? So we have these sort of typical accountability goals within cryptography. And the idea is like, we want to identify when things go wrong. So for example, failure of an assumption or failure of a protocol property. And then if possible, we also want to identify one or more of the culprits. And for this talk, I'll focus on scenarios where the sort of failure is not publicly visible. So don't think about things like double signing, which is publicly visible on chain, but rather think about examples where you want some party to prove failure to a judge. We'll sort of think about this as like a whistleblowing protocol. And I'll give examples in the future slides as well. But the idea here is we want one of the colluding parties to prove collusion to a publicly verifiable judge. So essentially, at a broad scope, you can think about this like whistleblowing framework as, let's say you have some n-party protocol that emulates a functionality. So basically, you have security as long as, say, t-1 parties collude. And if you have more than t parties collude, then security breaks. And sort of the idea of whistleblowing is that if you have some t-sized collusion here so that the protocol will ideally break, then a whistleblowing scheme will allow one of the parties inside of this collusion to obtain this sort of publicly verifiable proof of collusion that they can show to a whistleblowing mechanism or a judge and can sort of get a reward that way. So the judge can execute rewards or penalties. And we'll sort of focus on situations where the judge doesn't require any private state or tracing key, for example, to execute these rewards, so that it can itself be deployed as a smart contract. you sort of, for this whistleblowing, you want to kind of integrate two things together. One is this cryptography question, is when is it possible for cryptographic protocols to produce this sort of whistleblowing proof of collusion? What protocols can support such a proof? And there's this natural mechanism design or game theory question, which asks, are colluding players even incentivized to submit such a proof? So if there's a collusion and I obtain a proof, is it better for me to actually submit this proof or just stay silent in the first place? How do we think about rewards and penalties for that? And for this, we'll also model what I'll call a new smart contract-based collusion technique. I'll call this smart collusion. So I'll sort of focus mainly on the mechanism design side of things in this talk, but I'll quickly talk about sort of natural whistleblowing properties in general as well. So the properties that you want from whistleblowing protocol, kind of obviously we want some notion of completeness, which just means that if these T parties collude, then one of them obtains this whistleblowing proof. There's a soundness property that says if there's no collusion of large enough size, then no one will be able to obtain a proof that convinces the judge. We can have sort of this unframeability property, which is specifically useful for proofs that can identify colluders. So this is sort of a strong property that says even if everyone except for one honest person colludes, they still cannot blame this honest person. So this is sort of this like unframeability property.
So what does it mean collude here? Like, suppose I just share we have any arbitrary honest protocol, and T players share their internal states, which is not an instruction in the protocol.
Yep.
So thus they have colluded,
Yep.
but they follow the next message of the protocol. So in that sense,
so anything that they deviate from the colluding protocol, from the honest protocol, you can say they've colluded. Let's say.
but that's what I'm saying. Me sending to you my private state over a private channel, that's violating the honest protocol.
Yes.
However, that's undetectable. It will be indistinguishable from another observer.
Yeah, so I mean, we can assume sort of, for these sort of cryptographic properties, we can assume an adversary, like a powerful adversary just controls all of these n-1 colluders. So it's just one entity, right? For the game theory part, we'll separate out this adversary. Instead of considering one giant adversary, they'll actually be individually rationally players. But for all the cryptographic components, we can think about it as just one adversary controlling all of the malicious players.
I mean, maybe there is a way to think about it, like consider an execution where the output of the protocol is different than everyone was honest, and then you want to go back and find out sort of why, or I mean, like I think Abhi's point is kind of like that's a collusion which is like doesn't have an effect
impact
on the protocol execution, and so you can start from the assumption that the collusion changes the protocol.
So in some sense, you don't need to, right? Because even if you send that sort of private state and it doesn't change the output, then you can't frame anyone else.
The
right,
last property, yeah, fair,
Right.
fair, yeah.
So the problem is if you're doing a multiple instances of same sort of, let's say, threshold signature, we can collude in one iteration, but not deviate from the protocol, but thus learn, for example, a secret key or learn some secret information, and then in the next instance, use that to pick our inputs, for example, again, following the honest protocol, but like if it was a coin flipping protocol, for example, with some sort of like setup state or something like that, you could learn something in a way that's indistinguishable in the first iteration and use that knowledge in the second iteration to, for example, bias the coin flip. That's an example of collusion where you still follow all of the protocol instructions.
But can you frame sort of an honest party? So I don't fully understand like how you can use that to attack like a whistleblowing.
You break the correctness of the whatever protocol. I mean,
but then that's just sort of the security of the protocol itself. So for example, for this purpose, just think about a single execution protocol rather than executing like multiple instances of the same protocol as well, right?
But
So
I feel like he's talking about completeness, right? He's saying like, why wouldn't like completeness be violated in that example?
So then that wouldn't be like a whistleblowing protocol. If you can't get a proof, then that wouldn't be a valid whistleblowing protocol.
do you have an example of a natural? So do you have a result that says, given any protocol that's like whatever normally sound, like complete and sound and so forth, you can compile it into a whistleblowing protocol? Or is there just like a subset of protocols that support this type of thing?
Yeah, there's just a subset. We don't have like a generic result, let's say. We kind of looked at some natural applications that kind of by design support whistleblowing. And there's also some recent work that tries to build sort of these style of whistleblowing protocols for specific applications. And then we also focus mainly on the mechanism design of how do we even incentivize these proofs. So basically on the mechanism design side, you want some sort of incentive compatibility that like playing the honest strategy is some sort of subgame perfect Nash equilibrium. Yes?
Yeah, I also feel the completeness property as written seems a little too strong, right? So then for any protocol, if T parties just send a message, good evening, right? That how can you generate a proof that they deviated?
So in some sense, it's like if T parties collude to break the property, is that what it should actually be, right? So it's not just like T parties just talk to each other and they automatically get a collusion proof. It's that if they use it to break the property, right? So it's sort of like a broad framework that can actually capture a lot of natural applications. So we have some new applications specifically where like a server or a set of servers are providing a client with some computational service, and you want to prevent them from colluding with the client. So you can think about, for example, distributed randomness beacons that is provided as a service from a set of servers. And you want to ensure that randomness is not leaked earlier to the client, so they don't generate the randomness and give it to the client in advance. Or sort of like these rate-limited credentials or tokens where you want to ensure that the set of servers are not giving extra credentials to the client. So in each of these cases, sort of the client who receives this extra service through collusion will naturally obtain a whistleblowing proof. For example, in the randomness case, they can show that they have access to this randomness before it was supposed to be generated. But it also captures a lot of recent works on accountability for classical primitives that have been done in the past few years. So for example, there's this new primitive of secret sharing with snitching, which generalizes or extends secret sharing rather, so that if the colluders collude to reconstruct the secret earlier than expected, then one of the colluders gets a proof that there was a collusion. For example,
isn't the proof just the secret?
Yes, essentially. So the idea here is that in a normal secret sharing protocol, you can collude with MPC. So they can collude and use the secret without actually reconstructing it. But in the secret sharing with snitching protocol, the idea is you have to reconstruct the full secret to one entity in order to be able to use it externally as well. So there's also this new primitive accountable threshold decryption, which can prove that colluders decrypted some encrypted message ciphertext early. And this can apply to sort of privacy-based MEV minimization approaches, for example. It can also work for sort of BFT, some class of BFT forensics protocol, where an adversary can get a proof that more than, say, n over 3 servers colluded. And this kind of broad framework allows our game theoretic results to apply to a broad range of these accountable cryptography protocols. So let me just get to the game theory model. So let's say you have this cryptography protocol that's designed so that you end up with a proof of collusion whenever T parties collude. So the question now from a game theoretic standpoint is, should you submit this proof or just keep it to yourself? So here's sort of the roadmap I'll talk about the game theory in. So you can think about this base game B is the incentives without any whistleblowing protocol, so just a natural primitive. And then you can think about this sort of whistleblowing game for setting up the rewards of the whistleblowing in a way that incentivizes whistleblowing. But then I'll show this sort of third stage, which is this retaliation game, which will model or sort of final smart collusion-based technique, which will essentially try to penalize defectors who try to whistleblow. So this will be done by colluders to strengthen their collusion and disincentivize whistleblowing. Okay, so if you think about the base game B, each player can either play honest or collude. For simplicity, I'll talk about only n out of n collusion, where everyone needs to be colluding for the collusion to go through. So here, the utility function for each individual player you can think of as follows. So if everyone plays collude, each player gets utility V. Otherwise, everyone gets 0. It's kind of easy to see that in just this pure game, collusion is a pure Nash equilibrium. So now, a cryptographer comes in and designs a way for players to provide this sort of proof of collusion. And we can sort of think about like the proof being publicly verifiable, so it can be verified by a smart contract. And you can also allow it to be anonymous, so the smart contract doesn't know who submitted the proof. And essentially, we can sort of think about it as a smart contract, as I said. And we have the game theory question of how do we design this reward mechanism. So sort of here's a basic design for, again, as the game without the smart contract-based retaliation. So you can think about each player deposits some value D into the whistleblowing mechanism. And now, after that happens, each player can decide whether to play honest or play collude. If there's a collusion, then each colluder further has the opportunity to play sort of whistleblow or stay silent. And then this mechanism can decide on the whistleblowing reward and sort of penalize or slash the other players accordingly. And because the whistleblowing is anonymous, we have to account for the fact that multiple players can submit whistles. Even a single player can submit sort of multiple whistles. So really here, R and S are functions of the number of whistles that are blown. And you can think about the deposit that's required as essentially the maximum of whatever slashing penalty you want to enforce. So there's sort of natural properties that you would want from these functions. So the first thing is, let's say we want no reward or penalty to be given when there's no whistles being blown. So this is sort of the honest case, right? We also want something like no money is created. So any reward that you give must be smaller than all the slashes that you're doing. So you're not sort of creating money. And another thing is like an individual whistleblower, in order to incentivize them to whistleblow, should be better off whistleblowing than not whistleblowing, right? So the reward from one whistle should be larger than the slash. And here's sort of an effective mechanism that works in a game without retaliation. So the high-level idea is, let's say you know the collusion utility that you get from collusion, which is V. So you just take a slightly larger deposit than that. If there's 0 whistles that are blown, you take no action. If there's 1 whistle that's blown, you essentially give the whistleblower a reward V plus n minus 1 times epsilon, and then you just slash everyone else. And if there's more whistles, you actually just give 0 reward and slash everyone at the same time. So why does this work? The idea is you sort of create a prisoner's dilemma-esque situation for whistleblowing. So it's always better for individual colluders to blow the whistle. But if all colluders whistleblow, then the colluders are worse off. So in all cases, it's sort of like a dominant strategy to just play the whistleblowing if you decide to collude. And what that means is you should not collude in the first place. But now I'll talk about this new strategy that colluders can use, which I'll call smart collusion, which is basically using smart contracts to strengthen the collusion by penalizing any defectors or whistleblowers. And the idea here is that smart contracts can be essentially used as commitment devices. So you can have the colluders create a contract C that holds a large retaliation deposit from each colluder, for example, larger than the deposit that they have to pay into the original whistleblowing mechanism. And the idea is that if anyone tries to whistleblow, all of this retaliation deposit will get burnt. And this sort of incentivizes colluders to stay faithful to the collusion and not whistleblow. And the idea here is that the colluders can actually decide on this collusion mechanism after the whistleblowing mechanism is announced. So they have this sort of last mover advantage. And the idea is you can use this to circumvent a lot of prior results in accountable cryptography.
If you go back 2 slides, does your mechanism burn money? For example, you lose D if there's 0 whistles?
No, you get that money back.
Okay, so the first bullet is if there's 0 whistles, you get D back. Everybody gets D back.
Yeah. So we have an impossibility result for this retaliation game, which is fairly straightforward to see, is that a smart colluder with enough money can always win. And the idea is, you just create a smart contract collusion with a very, very large deposit. So essentially, unconditional security is feasible without smart collusion, but it's not feasible with smart collusion. And the impossibility actually holds even when whistleblowing is anonymous and can actually identify all of the colluders involved. But we do have a sort of bounded positive result as well. And the idea being that you can have a small whistleblowing deposit held by the mechanism and can protect against a much larger deposit, which is sort of n times larger in this sort of smart collusion. And sort of the intuitive sketch here is that you'll collect D from each player and give the whistleblowing reward n times D minus epsilon. So essentially, the whistleblower will lose their initial deposit d and get n times d minus epsilon, so they'll get n minus 1 times d minus epsilon. And each colluder will sort of need to put in a deposit that's larger than the whistleblowing reward, because anyone could do the whistleblowing at this point. So in order to prevent them from whistleblowing, the smart collusion needs to hold a deposit that's larger than the whistleblowing reward. So essentially, you can take a deposit d from each player, and to attack this whistleblowing mechanism, each colluder needs to put in a deposit of n minus 1 times d into the smart collusion. And we give a sort of roughly matching lower bound for this as well. I'll just briefly mention that you can extend these to a t out of n collusion as well, roughly by replacing just all instances of n with t. There's a little bit of a subtlety here, is like we only model one concrete sort of t-size collusion that just comes up out of the air, and we analyze it. The game can get really complicated if there's sort of multiple collusions that can happen. Players can sort of move between collusions, or leave one collusion and try to penalize the other ones, for example. So just to summarize this part, we talked about a new smart contract-based collusion technique that can circumvent a lot of previous accountable cryptography protocols. And the TLDR here is you should think about incentives when building cryptography. Sort of just to recap in the last few slides, the question is like, where do we go from here, right? So I talked about a first principles approach to designing these secure protocols, and I want to talk a little bit more from a philosophical standpoint here as well. And the kind of high-level pitch I want to make is that we need broader approaches to defining security, not just for blockchains, but maybe for modern system security as well. And modern systems are becoming more and more complex than they were sort of the 80s and 90s when a lot of these primitives were defined. There's a lot of new applications that are coming up, and we should really think more critically about what security even means, and not just sort of build protocols in the same sort of drop-in attacker models from several decades ago. There's also new attacker capabilities now that didn't exist in the wild, at least several decades ago. So I talked about how trusted hardware, MPC, smart contracts can be used for nefarious purposes by attackers. So they're not just tools that security researchers should use, but they're also tools that attackers can use and should be analyzed as such. Another kind of futuristic thing that I see happening is what happens when we get to a point where AI bots are indistinguishable from humans. Now, can you generate like an army of AI bots to extract more value from a system than you should have been given in the first place? Maybe some notions of permissionlessness that we've worked on blockchain systems can come in handy when thinking about systems of this form in a world where AI bots are indistinguishable from humans. So we really do need new age cryptography. The idea is we need so much more, right? We need a multi-pronged approach that combines tools from many different areas. So what we really want is to think about security as a central goal, and how can we use ideas from cryptography, distributed systems, mechanism design and game theory, macroeconomics, maybe policy and law, social sciences, maybe many other things to kind of look at security as a central goal that we want to solve. And we're not really close to having like a overarching model of security, but we really should start thinking about more intersections of areas when thinking about security. And that's kind of the pitch of this talk. The second thing I want to talk about is sort of this inherent fickleness of our models that we look at everyday basis, right? So real world systems are very, very messy. And because these security models model something about the real world, they're sort of inherently incomplete, right? So the models that we have today may not be relevant or appropriate to reason about some decades into the future. And in general, cryptography makes a lot of assumptions when proving security. Some of these are sort of mathematical in nature, like say prime factorization or discrete log. But there's a lot of these sort of soft assumptions that cryptography makes as well, which are more likely to fail in practice. So things like non-collusion or trusted setup, or just like what's in the scope of the model versus what's outside, or thinking about incentives, right? And we really should think more carefully about these soft assumptions when we're designing our security protocols. Really, the idea is like all security models, just like all statistical models, are wrong, but we want to think about what models are useful for existing applications today, and how do we think about security from this multidisciplinary lens. I'll kind of end there. Happy to take questions and also chat offline.
I would like to register my objection to using tic-tac-toe as the official icon for game theory and mechanism design.
Did I? Okay, cool. Any suggestions for what?
Yeah, I'll give you some offline.
Okay, perfect.
Definitely can improve on
Looking for slides. Yes, perfect.
When you model these the games with cryptographic proofs, generally the problem you have there is dealing with the soundness or soundness errors of those things. If you ever want to prove, so how do you abstract that? In other words, you can never say something's like a pure subgame Nash equilibrium.
Absolutely. Yeah. So we basically, for this purposes, we just assume like, it's perfectly sound, perfectly complete kind of thing. There's some really recent work from Bacillus, Sikas, and others that I really like of how to convert Nash equilibrium to sort of this like pseudo Nash equilibrium, where now you can analyze real cryptographic protocols. So you can analyze the mechanism design side of things with a completely ideal crypto functionality. And then when you substitute it for a real protocol, it still sort of goes through in this like pseudo Nash incentives context. Yeah, I'm happy to send you the paper if you're interested. It's not my work, but it's a work that I really like.
All right. Thanks again.